Hello students, so in this lecture we shall be talking about Dirac delta function. It is extremely used in quantum mechanics and is defined through the equation delta x minus a is equal to 0 for x not equal to a and a minus alpha integration to a plus beta delta x minus a dx is equal to 1, where alpha and beta are greater than 0. So, in words, we can say that the delta function has an infinite value at x equal to a such that the area under the curve is unity. Now, you can also represent this as a minus alpha to a plus beta fx delta x minus a dx is equal to fa minus alpha a plus beta delta x minus a dx is equal to fa, because this is equal to 1, as we have seen from this equation. So this is how you can also represent the delta function for any function f(x). Now, if x has a dimension of length, delta x minus a, the dimension of length inverse. Similarly, if x has the dimension of energy delta x minus a, it has dimensions of energy to the power minus 1. Now there are many ways by which we can represent the delta function. There is a way called rectangular function or rectangle function, R alpha. R sigma x, and it is defined as R sigma x is equal to 1 by 2 sigma for sigma x in between minus sigma x minus a between minus sigma and 0, and is equal to 0 for mod of x minus a greater than 0. If you plot this function, it is like this. This will be for sigma is equal to 0.4. This will be for say 0.1, and this is for say 0.04. So the lower we put the value of sigma, the more steeper it becomes. Sigma x, and this is the value of x, so this is 2. This is 1 and this is 3. This is how this rectangular function looks like. So if we take the integral of the rectangular function, means from minus infinity to plus infinity r sigma x dx, then this is equal to 1 by 2 sigma a minus sigma and a plus sigma dx. This is equal to 1. So we can imply that for sigma tending to 0, r sigma x becomes more and more sharply peaked, but the only difference that the area under the curve remains unity. So for sigma tends to 0, the rectangle function has all the properties of delta function, and we can say delta x minus a is equal to limit sigma tends to 0 or sigma x. Now take the integration minus infinity to plus infinity fx r sigma x dx, then this becomes equal to 1 by 2 sigma a minus sigma and a plus sigma fx dx, where we have assumed this function to be continuous at x is equal to a. Assumed fx to be continuous at x is equal to a, and this we can say that when sigma tends to 0 in the interval minus infinity x minus a minus delta minus sigma x minus a to x minus a falling between minus sigma and plus sigma, fx can be considered to be a constant is equal to fa, and it comes from the relation minus infinity to infinity x delta dx is equal to limit sigma tends to 0 minus infinity to infinity fx r sigma x dx is equal to limit sigma tends to 0 1 by 2 sigma fa a minus sigma a plus sigma dx, and this is actually equal to fa, so it proves the point that fx is equal to a constant on integration. So this is all about the rectangle function. Now another way by which we can represent Dirac delta function is Gaussian function. Gaussian function is given as g sigma x it is equal to 1 by sigma root 2 pi exponential minus squared x minus a squared, where sigma is greater than 0, and it can be plotted if you plot this Gaussian function with respect to x. It takes the value like this. This is for sigma 0.4, this is for 0.2, and the steepest one is for 0.1. So similar to the rectangle function, also we are getting with increasing value with decrease. So this is for 0.01. For decreasing value of sigma, we are getting a steep plot of this function. And this is again is 2, and this is 1, and this is 3. This is how this Gaussian function looks like. And we can also see that if we take integration, that means minus infinity to infinity. So this is also equal to 1. So it implies that how the steepness will increase with the value of sigma, but the area under the curve is always equal to 1. And another thing is that it has got a width, that is a bandwidth, which is the order of sigma at x is equal to a. Sorry, not at x is equal to 8. It has got a bandwidth of sigma, and at x is equal to a. So, right, at x is equal to a, the value of g sigma x is equal to 1 by sigma 2 pi. So that is, if you put the value of x is equal to a here, automatically this becomes equal to unity, and we are only left with this value. So 1 by sigma root 2 pi is the value at x is equal to a. So in the limit of sigma tends to 0, the limit of sigma tends to 0, this has all the properties of the delta function. So we can again represent the delta function in terms of Gaussian function in the following manner. We can say that delta x minus a is equal to limit sigma tends to 0, 1 by sigma 2 pi, and then here we can write exponential minus 2 sigma square x minus a whole square. This is actually the Gaussian function we are writing here. So this is how this delta function can be represented. So we have discussed two ways of representation of the delta function. Another way of representation is called the integral representation. So simply write here delta x minus a is equal to 1 by 2 pi minus infinity to infinity exponential plus minus ik x minus a dk. Now this value, now we know that 1 by 2 pi minus g to g exponential plus minus ik x minus a dk, this is equal to sine g x minus a divided by pi x minus a. Using Laplace's transform or complex variable technique, we can also write that 1 by pi minus infinity to infinity sine g x minus a, that means this one, divided by x minus a. We are not taking the pi here, we are taking the pi outside. So dx, this is actually equal to 1 for g greater than 0. And also we can write limit x tends to 0 sine gx divided by pi x minus a by x is equal to g. So we can imply that for a large value of g, sine g x minus a divided by pi x minus a is sharply peaked around x is equal to a, and as a unit area under the curve, and again the area under the curve is unity. So this is quite common in the case of delta function. Area under curve is unity. So if you plot it, you get the following representation. So this is how the function will look like for, say, g is equal to 0.5 and for g is equal to 5 and if we increase the value to say g is equal to 20, it will look something like this. So this is for g is equal to 20. Okay, that's with respect to x, and this is 2 and 1 and 3. This is how this function looks like. So we can represent this delta function as we just put limit here, and we put g tends to infinity. This function is equal to delta function. Now there are some important properties of delta function. Properties of delta function. First one being delta x minus a is equal to delta a minus x. Then fx delta x minus a is equal to fa delta x minus a, and minus infinity to plus infinity integration fx delta x minus a dx is equal to minus f dash a, and delta cx minus a is equal to 1 by mod c delta x minus a, where the c is a real number, is real, so is real and not equal to 0. Now there are some conditions in quantum mechanics based upon this Dirac delta function, and like if there is a wave function psi nx and it is from a complete set of orthonormal function, in the domain minus infinity to plus infinity, then the orthonormality condition we require that minus infinity to infinity psi m star x psi nx dx is equal to delta mn. This delta mn it is called the canonical delta, and it is equal to 1 for m is equal to n, is equal to 0 for m not equal to n. Now, since sin x is in complete set of function, we can expand an arbitrary well-behaved function phi x in terms of psi x. A pretty well-defined function phi x can be written in terms of psi x is equal to integration n is equal to 0, 1 to 3 to infinity Cn psi nx and to obtain the value of Cn, what we do, we perform the following operation. We integrate minus infinity to infinity psi m star x phi x dx. So putting the value of phi here, we get n is equal to 0, 1, 2, 3 to infinity Cn integration minus infinity to infinity psi m star x into psi nx dx, and as you know, this is, as we have seen, this is equal to the canonical delta mn. So you can write, and this is equal to integration n is equal to 0, 1 to infinity Cn delta mn, and that makes it equal to Cn. So similarly, we can also write Cn as equal to minus infinity to infinity psi n star x into phi x dx. So substituting these values of Cm and Cn and phi x, so phi x can be written as equal to minus infinity to plus infinity dx, sorry, n is equal to 0, 1, 2 to infinity minus infinity to infinity psi n star x phi x dash dx. dx dash into psi nx. But when we are just putting the value of Cn, this value that we obtained, we're just putting the value into this equation that we obtained, just transferring the value here, and we are getting this value of psi x. So this can be again be represented as equal to, let's put it in a different page. You can write again psi x as equal to phi x as equal to minus infinity to infinity dx dash phi x dash into summation n is equal to 0, 1 to infinity psi n star x dash into psi nx dx. So comparing with Dirac delta function equation, we can obtain an equation in the following way. We can say that summation n is equal to 0, 1 to infinity psi n star x dash into psi nx is equal to delta x minus x dash, and this is known as the completeness condition. That's the completeness condition, which an example. Let's take an example. Suppose we say that we take a function, it's called a right cross function, which is represented as psi nx is equal to n h n x to the power minus half x square, where n is equal to 0, 1, 2. This is your wave function. It's called Hermite-Gauss wave function, and here n this is equal to 1 by root to the power n by 2 to the power n into n factorial. We obtain the value of psi nx, that is equal to 2n plus 1 divided by 2 to the power half into pnx and we can write 1 by root pi sigma n 1 by 2n n factorial h n x h n x dash into exponential minus 1 by 2 x square minus x dash square, and it is equal to delta x minus x dash. So this forms a complete set of orthonormal functions in the domain minus 1 to plus 1. And to plot the function n is equal to 0, 1, 2 to infinity 2n plus 1 by 2 pnx to pnx dash is plotted, so it will look something like this. This will be 0 and our function should be for n is equal to 12 and for a higher value of n, say 20, much steeper one. So this is for n is equal to 20. Now this Dirac delta function is actually a distribution. So this another property of delta function is it is actually a distribution function. And to understand this, we first write the Maxwellian distribution. Recognize n mu is equal to 4 pi n 0 to n divided by 2 pi kt to the power 3 by 2 into psi square exponential minus n v square by 2 kt, where k is the Boltzmann constant, d is the temperature. Now this value n mu d mu, this represents the number of molecules whose speed lies between v and v, because this is not v, this is v. So number of molecules whose speed lies between v and v plus pv. So the total number of molecules will be just and integration of from 0 to infinity n nu d nu and actually get this value to be equal to say n naught now this is just a number. This n0 is just a number, and the function n nu, this has got a dimension for velocity to the power -1. So we can actually represent this nu in terms of Dirac delta function. That is, we can write n nu as equal to 4 pi n0 n by 2 pi kt to the power 3 by 2 multiplied by v square exponential minus mv square by kt. This is exactly how it was previously. Only thing we have placed it by n0 in terms of rather than n, and we add an extra term here plus n1 delta v minus v1. So this is the Dirac delta function and has the dimensions of universal velocity. So it is based upon the fact that we are considering that n1 molecules will have a speed v1, and the total number of molecules is of course n0. So this is how this representation of n in terms of the velocity v can be written in terms of this Dirac delta function. And the next part is how to represent Dirac delta function in 3 dimensions with 3D delta function. Can be written as, instead of using x, we can be using r. So the equation will now be delta r, which is a vector quantity, r minus r dash is equal to delta x minus x dash into delta y minus y dash delta z minus z dash. This is the first one, and again the triple integration fr delta r minus r dash, each for x, y and z, d tau, the volume element. This is equal to f r dash. This is the way we can write, and of course this delta tau, this means is equal to dx dy and dz. So this is all about delta function.